Hey, all right, students, I got a request to work on number 14 here. So let me give it a try. Let's see. Let's read it here together. It says, determine the magnetic field in terms of I, A, and D at the origin due to the current as shown in the figure. Well, maybe I better grab the book here and start off. And I set it up here on page 838. This is the Bieps of Art Law, and here's what it says. It says that a small magnetic field is made from a current. Of course, the strength of that field depends how far away you are, so that's what the R is. But it also depends upon some vector, and here is another cross product we're working with. And so let me kind of show you in this picture. This is what you saw in the lecture part of the videos here. But this wire here in brown carries a current, and that little section of current ds will make a magnetic field, and it'll make a field all the way around it, just like a point charge. So this Bieps of Art, this little equation here, is kind of like the equivalent of Coulomb's law. Coulomb's law, we know what the field is from one little chunk of charge, and then of course if we have something more complicated, we can add all those together to get the total field. So here we are. We're saying that little bit of current would make a field everywhere. Let's take a look at the field at point P here. And so you would do this calculation. These first ones are all constant. This is the permeability of free space, the mu naught, the 4 pi. I is how much current is flowing here. Well, that makes sense. How much current determines how strong the field is. How far away you are, and so the distance from that current to this point P would be the R. And then there's this little vector. This ds is the direction of the current, and this r hat is the direction to this point in question. So this r hat would be right here. Now, this video is not about how to actually do that one, so I'll skip the detailed mathematics of going through for a straight wire, but only because your author then did it for you right here on the next page, example 31. Your author says, okay, let's go ahead and take a look at, and he does this straight wire. And you can see here that this would be the ds, this would be the r hat. He's trying to find the field up here at some point P, so the r would be the distance, and then he's going to add them all up. So he goes through the math here, and again, let me not take the time here in this one to go through the math. I guess I did do that in the class lecture here. But he ends up with this equation. This is the important piece I want to get at, is then this is the equation that you want to keep in your mind that you would always use if you're trying to find the magnetic field from a straight wire. Okay? So I'm gonna write that down here as my first step in solving this equation and this problem. Now, before we leave this example here, let's make sure we really understand what all these symbols are. Now, remember, the mu naught is just a constant. That's this number back here, the 4 pi times 10 to the minus 7, the permeability of free space, okay? 4 pi, I think you know. I is the current in the wire, so again, this is only for a straight wire. What's A? Well, come back to this picture here, right? A, then, is this distance from the wire up to that point. And I would say it's the perpendicular distance. So if the point P was, say, over here, we would, draw a perpendicular distance. Okay? Or maybe up at this point here, this would be the A, the perpendicular distance, or this would be the A, the perpendicular distance. And by the way, maybe it's not very clear as he does the example, but there's nothing special about where he puts point P, or maybe put another way, there's no special place where he put the wire here. And so you could shift this wire all the way over to here. So point P could be to the actual left part of the wire. And I guess that's right of the wire. And then it would be that perpendicular distance. And then you might say the line of the wire, because the wire is over here somewhere. Okay, it could be the other way around. We can move the wire all the way over to the right, so the point is to the left. And again, it would be this perpendicular distance from that line. Okay, so keep that in mind. And then, of course, also keep the angle in mind. And so the theta 1 and the theta 2. So theta 1 is kind of a sweeping over how far from the point. So if I were to draw a line from the point to the end of the little wire, that'd be theta 1. And from the point of interest to the other end of the wire would be this theta 2. And they're measured from this perpendicular straight down, and that's that distance A. So we need to really understand where this came from, because I'm going to take a use of it here. And that's my suggestion here. So knowing all those, let's then come to this problem. So number 14 actually has this picture. And as we look at this picture, maybe you'll see now how I'm going to take advantage of it. I'm trying to find the field right here at this origin. And I've got this infinitely long wire coming here. And doesn't quite make it. It falls short by a little distance of D. In the vertical direction. Then it cuts across just above the x-axis, and some distance D above, and then, from a minus A to an A, there's the wire there. And then it goes back on up. So what I hope you see in 14 is that it's made out of 3 straight wires. So this is the equation for 1 straight wire. So I'm going to then say, all right, to get the total, I'm going to have the field from the first wire, and the field from the second wire, and the field from the third wire. And so maybe I should now, label them. Okay. So if I say this comes down, let's call this wire number 1. Then it cuts across. Let me call that wire number 2. And then the current goes back up. Let me call that straight wire number 3. And then they say, okay, so here's the current I. Now, we know from previous chapters about conservation of charge, Kirchhoff's laws, that the current I would then have to go across this way. So it's the same current I, and then it would have to go up. So we can conclude from our previous chapters that the current is I everywhere in this loop, if you will. And again, we're trying to find the field. Maybe I'll just put a little point right there, because this distance here, your author labels D, and this distance out to here would be A. He calls this minus A, and this over here plus A. All right, so I'm going to go ahead and do wire number 1 first. And maybe to understand it better, I'm going to twist it on its side here, so it looks like that picture we had. Let me turn back and see. Now it looks like that. Now again, in this case, the wire has been shifted over a little bit, but here's what it would mean if you were, I guess, drawing wire number 1 by itself. You would say, okay, here is wire number 1. It starts way out here at infinity. It comes to here, and I'll stop there. That's just wire number 1, and the point of interest would be up and over. Right there, point P. So again, so here's the wire, and we go up A and over D. So this would be up A over D. All right, so now to make this long wire, again, look like that picture. Let me draw some angles here. but because we said theta 1, and you need to find the perpendicular distance. So this goes down here. So there's A. And if I draw a line from the point P to the beginning of the wire, that's theta 1, it would go something like this, way out to infinity. So let me call that 90 degrees. And so theta 1 would be our 90 degrees. Let me kind of show you in the book again here, right? This is what they're talking about from the point down to the wire, or the line of the wire in this case. And then theta 1 is from the point to the beginning of the wire, way out here. So theta 1 is going to be a 90-degree angle. And theta 2, maybe I'll do a red color for it, would be right here. So this would be a theta 2. All right. So if I wanted to do the magnitude of field number 1, using this equation, it's mu naught times I over 4 pi. Now, I better be careful with my symbols. Remember, when we wrote this equation, A is that perpendicular distance. So in this problem, that would be A. All right. I just wanted to double check to make sure it wasn't D or some other symbol. Okay. Then it would be the sine of 90 degrees. So here's theta 1. Remember, the 90 degrees is this green line out to here. Minus the sine of, and here's where, again, a little careful here. If the angle swings this way, it's negative, and if it swings this way, it's positive. So in my case, and you can see that when they derive this, so theta 1 is a positive 90, as I wrote down, but also theta 2 would be a positive, not a negative, like they did in the problem, okay? Because they had the wire situated that the angle swings the negative direction, and it's positive when they go this clockwise direction, and negative when you go the counterclockwise direction, which is kind of the opposite of tradition. So that could be a little annoying. Anyways, this would be then sine of theta 2. Okay, let me just say that's the magnitude. Well, maybe I'll do one simplification here. Mu naught I 4 pi A, because this sine of 90 is 1. And also minus sine theta 2. If you look at this little triangle that's made with this red and this green here, sine of theta 2 would be opposite, so it would be this distance, so that's D, over its hypotenuse, which is this length. So the opposite would be the magnitude of D, this distance here. And its hypotenuse, that red distance, I could use Pythagorean's theorem here. There's an A and there's a D, so the sum of the square of the legs. So that would be A squared plus D squared square rooted. All right. So let me not box it, but just put a circle on it in a page 1, saying, okay, so there's the first step. Now, let me do that yet again, and I'll call this number 2. And then maybe wire number 2 I might want to look at kind of flipped upside down here, okay? Although that can be confusing because now the current's going to go in the other direction. But let me again just say this is the magnitude of it. I'm going to worry about direction here in just a second here. So this, when it's like this, other than it's going in the wrong direction, it looks a lot like this straight wire. Again, I just have the current going the other way. And so as we can see from a cross product, and we'll figure it out, that's going to make a magnetic field pointing in the opposite direction, now that the current goes in the opposite direction. But let me leave that alone for just a moment. Let me just say then that I have this wire now. Okay. And I will put the direction of the current just to remind me it is opposite. But if I were to draw then the perpendicular distance, that would be here, and that would be a distance of d. And we would come over an A and an A. And so if I were to draw theta 1, this would be theta 1. And then over this direction, this would be theta 2. So this here is theta 1, and this here is theta 2. All right, so now if I apply this equation we got for a straight wire, I would have the mu naught times the I. And I guess technically you might say minus I. Let me just kind of leave that alone. Like I said, I'll worry about direction a little bit later. This is the magnitude of the field, okay? So coming from wire number 2. And again, remember what A means. It's the perpendicular distance. So in this problem, or this wire of the problem, that would be D. And then we would have sine theta 1 minus sine theta 2. And again, let me do another simplification. As you look at this sine of theta 1, it would be the opposite. So that would be this distance, which is A, over its length, which, again, this would be distance D, this would be A, so Pythagorean theorem would give me an A squared plus a D squared, and then the square root. Now, I'm going to take advantage of a little bit of property of trigonometry. Sine functions are odd functions, meaning the sine of negative theta is the same as negative sine theta. And the reason I'm going to take advantage of that is because now, for this one, theta 2 is a negative angle. So instead of putting it in here as a negative angle, I'm going to put the negative out in front. And then with a negative already there, that makes a plus. All right. So the magnitude then of theta 2 would be the same thing as 1. It'd be the opposite A over this hypotenuse, which would be A squared plus D squared square rooted. So the magnitude would be this mu naught, this A, and now it looks like we have 2A over 4 pi D square root of A squared plus D squared. And that'll be number 2. All right, so moving on to number 3. I'm hoping you'll see that number 3 is really like number 1. Now, maybe the current goes in the other direction, so we'll talk about that direction, sure. But if you were to draw it, you'll see that the point of interest from the current is up A and over D. And so if I were to kind of do this direction for the current, it would look something like this. The current would start here and go over to infinity. And the point of interest would be up A and over D. And then the perpendicular distance away is A. So just like in number 1, we would go mu naught I 4 pi, and we'd put an A here for the distance away. Okay. In fact, maybe I will here. I'll put a mu naught, an I, and a 4 pi A. Okay. Now, well, I should probably draw the perpendicular distance right here. Okay, so here's the perpendicular distance from the line of the current. But now what I would do is I would put here from the point of interest to the beginning of the current. So this right here would be a theta 1. And maybe I should have done it like before in green. Okay, so here's a theta 1. And then the theta 2 would be from the point of interest to the end of the wire. Well, that's way over here. And that's about a 90 degree. Okay. And so I would put something like this, sine of theta 1. But now here's where that comment about which way does the angle swing come into play. This would actually be the negative of the magnitude of theta 1 because this is the negative angle. And then this would be minus the sine of a negative 90 degrees. And then I'll take advantage of the standard odd function here, because right here I can write this as those two negatives together as a plus, and it's the sine of 90, so that's the 1. And then I'll put the minus of theta 1 out in front, and for theta 1 I'll do opposite, which is this distance d here, over the hypotenuse, which is a squared d squared square rooted, and then I'll have the mu naught I over 4 pi a. And so, not a surprise, that is the same answer we got for number 1. I guess it's slightly different in the sense that the point of interest is now over here to the left of the wire, where in number 1, the point of interest was to the right of the wire. And because of that, we had two positive angles for wire number 1. And here we have two negative angles. But they also switched roles. And so if you were to change the sign of each of these angles and change their roles, because of that negative, you've got a double negative, and it comes out to be the same thing. So, not a surprise that they come out to be the same. All right. So, back to the beginning of this problem, here's what we have to do. We have to add up these vectors. And so far, I've just given you the equation for their magnitude. I haven't really said anything about their direction. So, taking page 1 and 2, and it looks like I'm out of yellow paper here. Let me grab another one real quick. I could then say, now let's write it as a vector. So, number 1 would be what? Well, we got its magnitude, so let me write that down first. Mu naught I over 4 pi a, 1 minus d over the square root of a squared plus d squared. Okay, so there's the magnitude of it. Now we need to do the direction. And so your author was trying to say that you can get this in two ways. You can just go ahead and continue to use the old right-hand rule, which just says the direction of the current crossed the direction to the point. So remember, putting your fingers in the direction of the current. So back here in this problem, it would be like this, putting my fingers in the direction of the current. Then rotate your wrist so you can close towards R, and so that would just be a cross product here. And so my thumb's pointing up. So that's saying here at point P, the field would be up. Okay. Now, your author goes on to say that you could rewrite that as this kind of thing. It's a different right-hand rule. That's why I think it gets confusing, because there's more than one right-hand rule. I like this particular one. although it makes you learn a second right-hand rule. But it just says basically if you take your right hand and make the thumbs up symbol, so we're not going to sweep this time, so that's the difference. We're just going to hold it in this position. And this right-hand rule is for finding the direction of the magnetic field based on current. So if it's a straight wire, since your thumb is straight, pretend your thumb is the direction of the current and your fingers show you the direction of the field. It also works the other way around, that if the current is going in circles, then use your fingers for the current and your thumb will give you the field. So it's still the same, holding your right hand with the thumbs up symbol, okay? So for us, we have straight wires. So I'm going to use my thumb for the wire, and this will give me the field. And so if I come back here to page 1, I do the thumbs up symbol. And for current number 1, I would want to put my thumb pointing down on the screen here. And that would mean that the field would wrap around in this circular effect like my fingers. So that means over here to the left of this wire, the field would be going in. So I'll put a little X going in. And on the other side, the field would be coming out. And this point of interest is on this right-hand side. So that would say it's coming out. Had this point been over here, I would have said the field's going in. All right, so coming out, let me call that the K or the Z direction. So it would be a K hat. And so I'm going to say K hat for number 1. Now, since number 3 was a lot like number 1, let's talk about it for a moment. Number 3 had the same mathematical value. Okay, so here it is. But what direction is it? Well, come back to page 1. Let's do the thumbs up symbol again. And look at wire number 3. Wire number 3 is pointing up, so I'm going to point my thumb up. And so notice my fingers curl around, meaning that over here on the left, the field comes in an upward direction, and over here on the right of the wire, it goes down. And our point of interest is over here on the left, so it would be up again. So it would be just like number 1. So number 3 and number 1 not only have the same magnitude, but they also have the same direction. Okay, so I'm just going to put up here that this is also the same as field number 3. So 1 and 3 have the same magnitude. They even have the same direction, which might have caught you off guard because you see that the current is coming down for number 1 and going up for number 3. However, they're also on different sides of the wire, and that's why it changed. So there's 2 changes. 1, you change the direction of the current, and 2, you change the side of the current it is on. And those 2 changes are 2 negatives, if you will, and 2 negatives make a positive. All right, and then number 2 was different altogether. Let's see, where do we derive? Okay, so here's where we derive number 2. Mu naught I. Tempted to cancel off a 2 there. Let me hold off, though, because kind of like the 4 pi downstairs, it's the same as the other field. So square root of a squared plus d squared. So there's the magnitude that we derived. Let's talk about its direction. And so coming back here, I'll do the thumbs up symbol and put my fingers here. And my thumb is in the direction of the currents, which is, left to right on the screen. And so if you follow your fingers, they wrap around. So that means below the wire, it's going in, and above the wire, it's coming out. And the point of interest is below the wire, which is in. So that would be the negative k hat direction. So negative k hat direction. All right, so now I can finally put all 3 fields together. Since these two are the same, I'm going to call that a 2 mu naught I over 4 pi a 1 minus d over the square root of a squared plus d squared. And then this one, I'm going to put a minus, because of this direction is the opposite. I'm going to put a 2 mu naught I, 2 mu naught I a over 4 pi d square root of a squared plus d squared. All right, now I guess we can simplify. And now I can go ahead and cross off a 2 here. And notice that every term here, or the two terms here, have a mu naught and an I in him, mu naught and an I. And downstairs we have a 2 and a pi. We don't have an A here, so looks like we would be left with from this one a 1, and from this one, let me be careful with that A, so I guess I'll have to put a 1 over A. Let's see, did I do that right? Mu naught I, 2 pi, and then no A. So I'm going to put that A into here. I'm going to also put the A into here. And so mu naught, there's an A. And then there's the 2 pi, and so then this is a D over the square root of a squared plus d squared, square rooted. And I guess I'm kind of wondering how far the solutions go. I bet they get a common denominator, so let me do that. And it looks like the common denominator would be a and a d and a square root of a squared plus d squared. And so it would be all those together. And so this first term, I need to multiply by a d and a square root of a squared plus d squared. The next term already has an a in there, so I guess I'll multiply by a d, so that would be d squared. And, just realized I needed a k hat up here. Hat. And then this one looks like needs to multiply by an a, so that's minus an a squared. All right, and I think that's the best we're going to do. Although I suppose it is tradition, but then we got negatives. Why don't I do this? Why don't I factor out a negative, so this becomes an a squared plus a d squared minus a d square root of a squared plus d squared here. And I'll put that negative I factored out in with the direction. Just because it's kind of nice to write radicals at the end. And so this would be going into the page. And let me look at the answers quick. There's a lot of algebra here. Good. And then the author says this, 2 pi, yeah, all matches, good. Nice. And then away from you is what he put. Good. A little long, but hopefully a helpful video. Take care.